To understand how fiber optics works, we must first review some important characteristics of light. The visible light we are all familiar with makes up only a small part of the electromagnetic spectrum that encompasses energy from radio waves all the way up to X-rays and beyond. All electromagnetic waves move at the speed of light, which is approximately 299,000 kilometers per second. The difference lies in the distance between the crests of individual waves, known as wavelength. In the visible part of the spectrum, the wavelength of light determines its color. Optical wavelengths are measured in nanometers, or billionths of a meter. Blue light has wavelengths of around 400 nanometers, while red light is approximately 700 nanometers. The infrared area starts around 800 and increases to about 100,000 nanometers as it approaches the microwave region. It is the infrared area we are interested in for most fiber optic applications. When light passes through various materials, its velocity changes. Light traveling through a vacuum moves faster than light traveling through denser materials such as glass. The abrupt slowing of the light at the vacuum glass interface causes it to bend slightly. This effect is known as refraction. The degree of bending is dependent on the ratio of the light velocities in vacuum and glass. The ratio, called the refractive index, is symbolized by the letter N. Glass can be doped to provide refractive indices tailored for specific applications. Various wavelengths of light will respond differently to the refractive index of a material. When white light, made up of many wavelengths, passes through a prism, the refractive index bends shorter wavelengths like blue and violet more than green and red, resulting in the familiar rainbow display of colors. When a beam of light strikes a refractive material, the direction of the refracted light will depend on the angle of incidence of the light beam. As this angle changes, so does the direction of the refracted light. At a certain critical angle, the light no longer passes through the interface between the two media, but is reflected as if the interface were a mirror. The critical angle will be different for various materials and is dependent on refractive index. The critical angle is responsible for the interesting optical phenomenon that makes fiber optics possible. In 1841, Daniel Colladon was the first to scientifically demonstrate the principle of total internal reflection. His experiment involved collecting sunlight and piping it through a tube to his lecture table. A lens focused the light through a water tank and out along a water jet squirting from a small hole in the other side of the tank. Light entering the water stream at the critical angle between the air-water interface is totally internally reflected, allowing the water to act as an optical waveguide.